Okay, good morning, everyone. Can you see the whiteboard?
Yes.
Okay, so welcome. And today we have to consider a new situation. So far, we have considered specifically systems that are in series. We have seen simple systems and then systems in series, interacting, non-interacting. We have seen that when you have systems in series, you can simplify and consider the overall system whose transfer function will be the product of the transfer functions of the single systems. So if you have 10 systems in series, you have the product of 10 transfer functions. And so the system will be, the overall system will be higher order, will be sluggish. And we have discussed this, the implications, the practical implications of this. Now, a legitimate question is, what if we have systems in parallel? Systems that are in parallel, not in series. So something like this that you can see on the whiteboard. So to simplify the matter, we have two systems, first order, each one characterized by its transfer function. These systems are in parallel. So you have a certain input, f. We are always in the Laplace domain. We are talking in terms of the transfer functions. So this is the block diagram. This is what we call the block diagram system. So we have an input, or at this point, you know, this is basically a change in the input. This is a disturbance, f. We have a disturbance. We have that this disturbance hits the two systems that are in parallel. And here you have the output, the overall output, or the overall change in the output, the overall response. Why? Please note that you have plus and minus. This has a specific physical meaning. This means that the disturbance F is producing on the two subsystems a response, a reaction that go basically in different directions, in opposite directions. The effect of F on the first system goes in the opposite direction than the effect of the disturbance on the second system. And so the question here is, what is the overall response of the system? Let me make an example to consider, to understand a little bit better what we are talking about. Let's consider you have two tanks in parallel. You produce a disturbance in the inlet flow rate, and then you observe the level in the two tanks. And you observe that the level increases in one and, let's consider, decreases in the second one. So the input is producing two effects that go in opposite directions. That's why we have plus and minus. So what is the overall response of the system? Well, we know how to do this. Simply following the block diagram, the overall response, y, will be the transfer function of the first system times the disturbance, minus, because here we have minus the transfer function of the second system times the disturbance, which is exactly what you can see here. Each of the two systems has a static gain that is Kp1 and Kp2. Each of the two subsystems has a characteristic time constant that is tau1 and tau2. So the two systems are different. Now, what should we do? Algebra. Simply, let's calculate this. Let's manipulate this. So we can collect f, and basically we can subtract these two terms. We can subtract the transfer functions. If you manipulate algebraically this expression, you get something like this. So this will be the overall transfer function, that represents the overall system. Make sense?
Yes.
Okay. Now, please, guys, pay attention, because this concept is maybe a little bit tricky. So please, I need to ask you to pay attention, to focus very well now. Okay. Let's consider now the real response that we measure. The real response that we measure is not y capitalized in the Laplace domain, is y non-capitalized. We measure responses in the time domain. So let's consider the response of the system as a function of time. As I mentioned, the two subsystems will respond to the disturbance in a way, in two opposite ways, because there is plus and minus. Before we analyze the response, let's consider an hypothesis. Let's make an hypothesis. Let's hypothesize that tau2 is much larger than tau1. What that means that tau2 is much larger than tau1, please? That the second system is much. Please go ahead.
The second system will approach a zero faster than the other?
Will be slower. The larger the characteristic time, and the slower the system. So tau measures the sluggishness. And so the second system is much more sluggish, much slower than the first one. And let's hypothesize that the absolute value of Kp2, that the static gain, the absolute value of the static gain of the second system is larger than the absolute value of Kp1. What that means? This means that the second system is much more sensitive to a change in the input. This means that the second system will respond much stronger than the first system. Okay, now let's draw qualitatively the response of the system. So system number one, subsystem number one, the response to the disturbance is positive, and let's consider will be something like this. Response of the second subsystem. So the second subsystem is slower because tau2 is larger than tau1, so it will respond in a very sluggish way, and the response will be stronger because Kp2 in absolute value is much larger than K. And so qualitatively, the response of the second system will be something like this. Does that make sense for everyone?
Yes.
So this is indeed much sluggish than this. You know, it reaches a new steady state much in a very slow way. And basically the absolute value of the new steady state is much larger for the second system because Kp2 is much larger than Kp. So the second system is more sensitive to a given change in the input. Now, we are interested in the overall response. What is the response of the overall system? Simply is the sum of these two curves. If I sum algebraically these two curves, I get something that is like this. At short times, the first response, the response of the system 1, will be dominating. But at a longer time, asymptotically, the response of the system number 2 will be dominating. And so basically the response will be something like this. Does this make sense?
How did you get the red line? Is that just the composite of 1 and 2?
Yes. The red is simply the sum of the responses 1 and 2. Is the algebraic sum. Make sense?
Thank you. Yes.
So at short times, basically the response, the overall response is dominated by the response of the system 1. For longer times, asymptotically, the overall response is dominated by the response of the subsystem number 2. Make sense?
Yes.
Okay, so when we have a situation like this, we say that the system exhibits reverse response or inverse response. What that means from a physical point, that means, and we will make an example immediately, that when you apply a disturbance, the response will be first going in a certain direction, will be positive, and then it will turn negative, and it will go in another direction. For example, I increase the inlet flow rate, the temperature of the inlet flow rate to a tank, and basically the temperature in the system first goes down and then goes up. Is non-monotonous. Okay, now we want, before we make an example, we want to generalize. Can we devise a general criterion to identify when, under which circumstance, a system exhibits a inverse response? Simply, if you consider this generic transfer function, we may analyze this time the numerator. So far, we have always considered the denominator of the transfer function. We have always considered the poles. So the stability is determined by the poles. The response of a system to a disturbance is determined by the poles. The poles will tell you if the system is oscillating or not oscillating, and so on. Now, the inverse response is basically determined, is dominated by the numerator of the transfer. If we calculate the zero of this numerator, we get that the zero of this numerator is Kp2 minus Kp1 divided Kp1 tau2 minus Kp2 tau1. So, based on what we mentioned before, Kp2 is larger than Kp1. Tau2 is much larger than tau1. So this zero, the zero of the numerator, for sure is positive because it's the ratio of two positive numbers. So we can generalize and state that a system exhibits inverse or reverse response when its transfer function exhibit any, when the numerator of the transfer function exhibits any zero with a positive real part. If you calculate the zeros of the numerator and you get at least one zero with a positive real part, for sure that system will exhibit inverse response. Make sense?
Yes.
Yeah.
Okay, so please, at this point we have a very clear picture. The transfer function is really a powerful tool because both numerator and denominators basically will tell you a piece of story about the response of the system to any disturbance. So, do you want to know if the system oscillates or not? Do you want to know if the system is stable or not? Study the denominator of the transfer function and calculate the poles. And this will answer your question. Do you want to know if the system exhibits inverse response or not? Consider the zeros of the numerator of the transfer function, and this will give you the response. So the transfer function for a system is basically what you need to predict completely with the minimum amount of calculations how the system behaves. Let's make an example. We have a system whose transfer function is this: s squared minus s minus 2 divided s cubed plus 7s squared plus 2s plus 1. So the question is, does this system exhibit inverse response? You don't need to interrogate nuclear physics or complex theories. Just find the zeros of the numerator. And this is a very simple equation. The zeros are -1 and 2. So does this system exhibit reverse response?
No?
Yes, there is a positive pole. Sorry, a positive zero. Make sense?
Yes.
There is a positive zero. One of the zeros of the numerator is positive. Now, let's consider another scenario. Now, the denominator is the same, and the numerator is s squared plus 4s plus 3. So, does this system exhibit inverse response? Well, if the numerator exhibits any positive zero, yes. So here, the poles are -1 and -3. Does the system exhibit inverse response?
No.
No.
No, because both of these zeros of the denominator are negative. Or philosophically, there is no zero with positive real part. So you don't need to do experiments. You don't need to build up a system, do an experiment. You can predict immediately with a few steps, a few calculations, if the system exhibits inverse response or not. Now, let's make an example. Let's make an example. And let me switch for a few moments to the presentation, because this concept can be somehow complicated. Now, can you see my presentation?
Yes.
Yes.
Okay. So, okay, now, the question is, okay, this is a very nice theory, but please tell me a system in chemical engineering that exhibits inverse response. First of all, do we have many systems that exhibit this behavior? Not really. They are not common, but we have some typical situations. And one of these is given by the reboilers. Reboilers, they can really exhibit inverse response. These reboilers, as you remember, they are always there at the bottom of a distillation columns. I'm sure you remember this. Let's consider a situation like this. Let's consider the schematic that you can see basically here on the bottom. So you have this room, this basically this reboiler drum. You feed a cold liquid. You feed a cold liquid, and you provide heat to partially vaporize that liquid. And so in the reboiler drum, you have a mixture of liquid and vapor. If that is water, you have liquid water, and on the head space, you have some vapor, water vapor, steam. Obviously, some water vapor will dissolve into the liquid with bubbles, through bubbles that will basically blow the liquid. Okay, this is very simple. Now let's consider that there is a disturbance hitting the system. Let's consider that there is a step increase in the inlet flow rate. You increase following a step, basically the mass or the molar or the volume flow rate of the cold water. So, does the level into the reboiler, the level of liquid, increases or decreases? So obviously there your response, I'm sure, would be increases. I feed more liquid and the level will go up. I'm sorry to say that this is not true. This is a typical example when you have inverse response. If you feed more cold liquid, for a few seconds, you will first observe the level going down, and then the level will start to go up later on. Why is that? Simply, it's true that in absolute sense, you are feeding more liquid, more cold liquid to the system. However, the temperature in the reboiler drum for a few seconds will go down, will decrease. And so some vapor bubbles that are entrained into the liquid will disappear. So if vapor bubbles disappear from the liquid will shrink. The liquid will shrink instead of expanding. So for a few seconds, you will observe the level going down, even though you have basically you have fed to the system more water. However, in the meantime, you are continuing to provide heat to the system. So within a few seconds, the temperature will go back to the original value, and basically you will see the level going up. But this will happen later on, not immediately. Does this make sense for everyone?
Yes.
So the response isn't inverse in terms of the mass balance, but in terms of the height of the liquid it is.
Yes. Basically, there is inverse relatively to the level. Yeah. So this is a system, typical system, when you have this inverse response, but you have many others that we cannot mention because we don't have enough time. But another typical example, and you can check for curiosity if you are curious, is thermometers. Thermometers sometimes may exhibit inverse response. So it's not a very common behavior, but happens. And so if you observe this, don't be shocked, because you could be shocked. You may say, how is that possible that I am feeding more liquid and the level for a few seconds is going down? Is there a problem? Is there a leaking? No, it's simply a physical feature that follows from the consideration that we have seen before. Now, before we close and we move to problems and example, and before we can consider basically completed the first part of the class, the process dynamics, we may want to answer a few other curiosities, a few other questions. For example, can the static gain for a process, whatever the process is, first order, second order, whatever, can the steady state gain, the static gain, be negative? Or it must be positive, just positive? What's the story? It may be positive, it may be negative. Really, this depends on the situation you are considering. So if you face a negative steady state gain, don't be shocked. Is not because you made a mistake, but because the situation you are considering requires a negative static gain. Let's make an example. Let's consider the situation you have on the bottom of this slide. So you have a tank, and from the tank you withdraw some liquid. What happens to the level? The level goes down. So basically you are increasing the input, and basically you are decreasing the output. The static gain is negative basically when a positive change in the input produces a negative change in the output. When a positive deviation of the input from the steady state produces a negative deviation of the output from the original steady state. So in this situation, the outlet flow rate VO dot is an input or is an output? Is an input, because it's controlled with a valve, is a manipulated variable, so is an input. So if you increase VO dot, if you increase the input, the output, which is the level in the tank, will go down. A positive change in the input will generate a negative change in the output. And so, yes, this is a typical situation where the static gain may be negative. Okay, at this point, I think we can just go back to the whiteboard that you probably can see, and let's move to problems and applications. And with this, we can complete the first part of the class. Basically, we have completed the dynamic. We have focused so far on the process dynamics, and so in the rest of this course, we will focus on controls theory. Okay, so let's consider another example, which is the problem 15. The problem 15 in the list of problems that you have on Canvas. And to be honest, we started this problem last time. So a process is described by a transfer function like this. This is a parametric transfer function. So last time we saw from which value of k the system is underdamped. Now we want to calculate for which value of k the system has a decay ratio equal to 1/4. So just to recap, is this a transfer function written in the standard form?
No.
No, because here we have 1 plus k, and we need to have 1. So last time we saw in the standard form this transfer function will look like this. And that is the starting point. We have to start from here and not from there. Make sense so far?
Yes.
Okay. So when, for which value of k, the decay ratio is equal to 1/4? Simply, we have to, during the exam, when you solve the problem, you have your notes, you have the book, you have the handouts. Just look to the formula. You don't need to remember the formula, but just remember where you can find it. So the decay ratio, by definition, is basically the exponential of minus 2 pi psi divided the square root of 1 minus psi squared. And we saw this formula last time. You can find this formula, this definition, in the slide group number 7. So basically, this decay ratio, if you remember, will tell you how fast the oscillations are dampened in an underdamped system. So we have to find the value of k that makes the decay ratio equal to 1/4. First thing first, I would get rid of the exponential. So I would consider the logarithm of both sides. And so basically, in this way, we get minus 2 pi psi divided square root 1 minus psi squared equal to logarithm of 1/4, which is minus 1 and 3/86. And this minus and this minus can be suppressed. Make sense?
Yes.
Okay, so I will leave the expression of the transfer function here so that we may look at it. Then I would divide everything by 2 psi so that I can incorporate this 2 psi in this constant. And this will be written in a more compact form. Okay, but okay, very nice. But how should I incorporate k in this expression? Well, last time we found an expression for the damping factor. You may remember that last time we saw that the damping factor in this system is 3/4 the square root of 1 plus k. Do you remember this?
Yes.
So what we have to do is just take this expression here and replace in the previous one, so that the previous equation will become an equation in the variable k. So if you do this, you get 3/4 times the square root of 1 plus k divided the square root of 1 minus 9/16 times 1 plus k equal to 0.221. And so now you have an equation in the k variable. So now you can proceed as you wish. You can proceed with the Excel, with the Mathematica, with MATLAB. It's not important the way you use it to solve this equation. Just solve it numerically or analytically as you wish. And you get that k is equal to 11.08. So if k is equal to 11.08, the system represented by this transfer function will have a decay ratio equal to 1/4. Simply, this is a parametric study, which is very common in engineering problems. Make sense for everyone? Yes or
Yes.
no? Okay. Again, to solve this, I'm not really interested in how do you solve this. Just proceed as you wish. Excel, Mathematica, MATLAB, MathCAD, analytically, you are engineers, and so it's up to you.
I have a question.
Yes.
So the K that we solved for here is not the same as KP, correct?
No. This is a parameter. It's not KP. No. KP,
Okay.
KP will be, in this case, 2/1 plus K. Make sense?
Yeah, that makes sense. And that equation that you used to relate the psi to the K, is that only for underdamped systems?
No. This is specifically for this system. We retrieved this last time. Just look.
Oh, okay.
Look to the notes that you took last time. I didn't retrieve that again because we did this last time. Okay.
So it was, it's for this system that we're talking about.
Sorry?
It's only for this system.
Yes. This is specifically true for this expression. Simply, I retrieved psi from this expression here. Make sense?
Yeah, thank you.
Mm-hmm. Okay, now we can continue with a very interesting problem. This is a very good one. And this is the problem number 9. Problem number 9. Let us consider an irreversible first-order reaction occurring in an isothermal CSTR reactor, whose volume is 5 cubic meters. So, isothermal CSTR with the first-order reaction. What do you expect the order of this system to be? First order. An isothermal CSTR with the first order reaction, as we saw a while ago, is first order. So you already know what you have to get. If you know the theory, you know what you have to expect. And if you don't get that, you have to go back and check the calculation. So we have this CSTR, the volume is 5 cubic meters. So this is a very small one. This is a lab scale CSTR. The reaction is irreversible. A that gives B, first order, elementary. The feed flow rate is 1 cubic meter per hour. So 1 cubic meter per hour is really nothing. This is basically a laboratory CSTR. At a certain time, which we assume as the time 0, a step disturbance on the reactant concentration is imposed to the system. So the inlet reactant concentration is CAI. And we basically impose a step disturbance on CAI. Then the departure of the reactant concentration in the reactor or leaving the reactor is the same from steady state. So the departure of the reactant concentration in the reactor from the original steady state value, which means CA deviated, is reported in the following table. So basically, experimentally, you stay there for a few hours and you measure basically how the concentration in the reactor or leaving the reactor departs from the original steady state. And so you have a table with time in hours and basically the deviated CA. So these are experimental data. So with this information, the question is calculate the kinetic constant. So this is a possible way to calculate, to determine the kinetic constant. So this problem really englobes everything because we have to individuate a model, write the model, eventually linearize, write in the deviation variable form, transform, get the transfer function, apply the disturbance, and then see what the response will be. So it's very comprehensive. Okay, model. So how do we need to model the system? Is a isothermal reactor. So for sure, we don't need to interrogate the energy balance. I would start, the complete model would be basically the mass balance. And basically how many mass balances you can write here?
2.
2. You have 2 components, A and B. So you can write a maximum of 2 mass balances. One of them will be the overall mass balance. And the second one will be the mass balance or the molar balance for the reactant, for example, because most of the data are data on the reactant concentration. And let's focus there. Let's consider the part of the model that represents the molar balance for the reactant. V, derivative of CA with respect to time, equal to V dot, VI dot, CAI minus CA minus K V CA. First order kinetic, the system is isothermal, the kinetic constant is constant because the temperature is constant. Very easy. So now we can get rid of VI dot. We can divide everything by VI dot. V divided VI dot will be a characteristic time that we call TR. And here also this V will disappear to give rise to TR. Now we can write this in a more standard form. TR, dCA into T, plus CA, plus K TR CA, is equal to CAI. Makes sense for everyone?
Yes.
We can lump together these two terms. And now this differential equation is written in the standard form. Is this linear or nonlinear?
Linear.
Linear, because temperature is constant, so K is constant. TR is constant, basically, because the volume is constant. The volume is constant, the level is constant. And that's it. It's linear. We don't need to linearize anything. What's next step? We have to write in the deviation variable form. So basically, let's subtract the model written in the original steady state, subtract term by term, and we define CA minus CA star equal to CA deviated, which is exactly the experimental datum that we have, CAI minus CAR star equal to CAI deviated. Okay, makes sense for everyone?
Yes.
So this is very easy. Is an isothermal CSTR. Okay, next step. Next step is transform with Laplace. Transform with Laplace, and so we have TR S CA capitalized plus 1 plus KTR CA capitalized equal to CAI capitalized. And now, basically, we have that we can collect CA capitalized here. And finally, CA over CAI capitalized. This is the Laplace transform of the output in the deviation variable form divided the Laplace transform of the input in the deviation variable form. This is the transfer function, and so will be 1 over TRS plus 1 plus KTR. Make sense?
Yes.
So what is the order of the system? First order, as expected. So we are doing well. So is this transfer function written in the standard form? No, because this is not 1. This is 1 plus KTR. And so I have to collect 1 plus KTR outside, and then TR over 1 plus KTR S plus 1. Make sense? Make sense or not?
Yes.
So now let me lump this together. This is the transfer function of the system in the standard form. Make sense? So this is Kp and this is tau. Are you still there?
Yes.
Okay, good. Now, the statement says that we apply a step disturbance in the inlet reactant concentration, and then we measure the output. So, basically, in the Laplace domain, CA is the transfer function times the Laplace transform of the disturbance. So, if the step that we apply on the inlet reactant concentration has amplitude A, generic, basically CA in the Laplace domain will be A divided 1 plus KTR S times TR 1 plus KTR S plus 1. Makes sense for everyone? I simply multiplied the transfer function by the Laplace transform of the disturbance, which is A over S. This multiplied A over S gives rise to this expression here. Make sense?
Yes.
Yeah.
Okay. Now, this is basically the response in the Laplace domain. We have to anti-transform this back to the time domain. And this is a very easy anti-transformation, because you can find in the table the anti-transform of this. So CA deviated as a function of time, the anti-transform will be A over 1 plus KTR, which multiplies 1 minus the exponential of minus t over tau, where tau is tr divided 1 plus KTR. This is basically tau. Okay? Still there?
Yes, that makes sense.
Okay. So now, this is the response in the time domain, which is actually what you have in the table. So let's try to simplify this a little bit. If time goes to infinity, so if we consider the asymptotic behavior, basically this exponential will go to 0. And so basically the asymptotic value of the deviated reactant concentration, which is A divided 1 plus KTR, this exponential goes to 0. 1 minus the exponential goes to 1. So the asymptotic value of the reactant concentration deviated is A divided 1 plus KTR. Make sense?
Yes.
Now, guys, do you have in the table this value? Look at the table. Can you tell me, guys, what is the value of CA infinity? Don't be shy. Look at the table. Is 1. Is 1. Make sense? Are you alive? Guys, if you don't respond, I suppose that you understand. So if you have questions, please let me know. Can you verify in the table that the asymptotic value of CA deviated is 1? Can you verify this?
Yes.
Okay. Is 1. Is reported in the table. So CA, function of time, is A divided 1 plus KTR, which is CA infinity, which is 1, is a number. You have that in the table, times 1 minus the exponential of minus t over tau. And this is 1. This is 1. This is the asymptotic value of CA that you have in the table. You can see that the CA deviated starts from 0, and then it becomes 0.095, and then 0.0918993, and 1 is the asymptotic.
Dr. Galizia,
Yes.
where's this table at?
Sorry?
The table you're getting these CA values at, or that you told us to look up, where is it?
If you turn the page, you can find it in the table. Just turn the page. It's in the page after. Can you see that? So guys, do you have the table? Can you see the table in the statement?
Yeah, I see it.
Yes or not?
Yes.
Just turn the page. Can everyone see the table? Guys,
Yes.
please
Yes.
be a little bit reactive. We have to communicate. I cannot spend every time. Can you see the table? Yes or not?
Yes.
Okay, just turn the page. Turn the page. Make sure you have the statement with you. Turn the page and you will find the table there. Please, guys, we need to communicate. If I ask a question, please, it's nice to respond. Don't stay quiet, because it's difficult for you to make classes in remote, and it's difficult for me because I cannot understand if you are understanding. So please, let's communicate. When I ask a question, respond. So we have arrived to this point. So we have CA, function of time, and we have these values in the table. this is 1, and this basically is available in the table. And we have to find the kinetic constant. Well, let me manipulate a little bit this expression in this way. Basically, I can rewrite this in this way. Ca over Ca infinity equal to minus 1 minus the exponential of minus t over tau, which means the exponential of minus t over tau is equal to 1 minus Ca over Ca infinity. Let's consider the logarithm of both sides. Minus t over time equal to the logarithm of 1 minus Ca over Ca infinity. And that's it. We are done. We are done. So what you have to do now is report the logarithm. Just go in Excel and report the logarithm of 1 minus Ca over Ca infinity, and you have Ca and you have Ca infinity. Report this as a function of time. So just plot the data in the table in this form. What curve do you expect to get?
Should be a line.
A line. And a line with positive or negative slope?
Negative.
Sorry?
Negative.
Negative. So you will get a line like this. So what is the slope of this line?
Minus 1 over tau.
Minus 1 over tau. So go in Excel, plot the data in this way, get the slope with a linear interpolation, and the slope will be equal to minus 1 over tau. And so this means, let me write the equation of the interpolating line. Basically, I got something like this. The logarithm of 1 minus Ca over Ca infinity equal to minus 0.4971 times t. So basically, tau minus 1 over tau, the slope will be minus 0.4971, from which tau is equal to 2.012 hours. Make sense?
Yes.
So now we need the kinetic constant. And so what we know is that tau is Tr over 1 plus k Tr. And so we have to get k from this expression. To get the k from this expression, you need the tau, and we just calculated tau, and we need Tr. But do we have Tr, or can we calculate it?
We can calculate.
So how can we calculate Tr? Is V over Vi dot, which means 5 over 1 is 5 hours. Make sense?
Yeah.
So this is the equation. I have to get k, and I know tau, I know Tr, so I can get immediately k, which is 0.3, approximately 0.3 hours at the minus 1. So you are disturbing a small CSTR, and you are using this technique to get the kinetic constant for that reaction. This is one of the possible ways to get the kinetic constant. Probably you have discussed this with Professor Vesasco in the past. Make sense for everyone?
Yes.
Yes.
Okay, just. Okay, now we can proceed with the problem number 13. I'm not following necessarily the order. I want to provide now a general picture. However, by next week, before of the middle term, we will solve all of these problems and the solutions will be available on Canvas as well. What we have to do now, guys, is to make sure that we have a general overview. Now we have to put all the parts together and make sure that we have a general overview. Problem 13. Which of the following second order systems is equivalent to two non-interacting first order systems in series? So the first system is represented by this transfer function. The second system is represented by this transfer function. So, which of these second order systems represents physically the series of two first order non-interacting systems? So, guys, now I need your help. Need a little bit of interaction. How can I understand this? How can I figure this out? Obviously, you need to know the theory to solve the problem, as for any problem.
Well, we know the transfer functions for first order and series have to be multiplied by one another.
Well, we have to, for sure, a second order system will result from a series of two first order systems. However, we saw a couple of times ago that the series of two first order systems non-interacting gives rise to a second order system that is over-damped. Do you remember this?
Yes.
The series of two first order systems non-interacting is a second order over-damped systems. Two first order systems in series non-interacting gives rise to a second order over-damped system. So what should I do to figure out which of these two systems is given by the series of two first order non-interacting systems? Simply, I have to go.
You have to figure out if either one is overdamped.
That's right. Simply, I have to understand which of these is overdamped. One of them, both, none of them. Simply, if this is overdamped, this basically will be equivalent to two first order non-interacting systems in series. So, once again, with no theory, we cannot solve the problems. Not in this class, always in the life. If you want to solve a problem, you have to be knowledgeable. You have to know the theory. No theory means that we cannot solve any problem. If we try to approach empirically a problem, we won't go anywhere. So, is this transfer function written in the standard form?
No.
No, so I cannot say anything. So let me collect 2 and write this in the standard way. So now this transfer function is written in the standard form. So tau is clearly 1 over the square root of 2. And now to understand if the system is overdamped, I have to calculate the damping factor. 2 gamma tau is equal to what in this case?
3 over 2.
3 over 2. Just remember that for a second order transfer function, the general formula is this. So 2 gamma tau is 3/2. So tau is known, is 1 over the square root of 2. And so basically psi, the damping factor, is 3/4 times the square root of 2. And this number is approximately 1.06. So is this system overdamped?
Yes.
Yes, because psi is larger than 1. So this system is basically the series of 2 first-order non-interacting systems. So for sure, our system is not something like this. Our system is something like this, is given by the series of 2 non-interacting systems. There is no recycle. For sure, this system does not exhibit a recycle. So let's write the block diagram. To write the block diagram, we have to find the poles there. Basically, the poles of this denominator are -1 and -2. So I can write this transfer function as 1 divided s plus 1 times s plus 2. And so basically, this is the series of 2 non-interacting systems that gives rise to this overall overdamped system. Make sense for everyone?
Yes.
Okay. So likewise here, let me go very fast. Standard form of the transfer function, tau is equal to 1 over the square root of 2 psi tau will be equal to 1/2, from which the damping factor psi is equal to radical 2 square root of 2 over 4, which is less than 1. So this system is over critically or underdamped?
Underdamped.
Underdamped.
Underdamped. So this is not the series, or we cannot tell that this is the series of 2 first-order systems non-interacting. So the answer will be yes for this, no for this. Is there any question on this? No. Beautiful. So guys, we are closing for today. Just before you leave, there is an homework arriving. So in 1 hour, couple of hours, expect to see the homework number 3 on Canvas. Please, this time, follow the formatting rules. This time, not following the formatting rules will imply a penalization. Homework must be returned in Word so that I can comment, and these comments are useful for you. Okay? So I will talk to you in a couple of days.